We defined radioactivity yesterday as a spontaneous process, a random process in which a nucleus decays into something else, a new nucleus. Carbon becomes nitrogen, or uranium becomes something else, or gold becomes something else. Now, we talked about 3 types of radioactivity that can occur as a result of unstable nuclei, which, by the way, if we're talking about unstable nuclei, there's something like 2,500 different isotopes of elements, 2,500 different versions of elements, and there's something like 2,200, I don't have the exact numbers here, but something like 2,200 of them that are unstable, that are radioactive. The vast majority of nuclei are radioactive. The vast majority of isotopes are radioactive. And the reason is because, we saw yesterday, right? It has to be such a fine balance between numbers of protons and neutrons. You get too many protons, something happens. You get too many neutrons, something else happens. Too many protons, maybe something else happens. Okay? So in the end, you got to have this perfect balance of protons and neutrons to keep the forces good, to keep the energies good, and if you don't, then the nucleus is unstable, and at some point it's going to break apart. Let's talk about the 3 types of radioactivity. Let's talk again about that balance that has to be struck, and when the balance isn't struck, what happens? And then let's talk about some of the properties of those 3 types of radioactivity. Then we'll go into something called transmutation, which is describing the actual decay of the nucleus by looking at what's produced, what's left over, okay, what's the new nucleus that's produced, and then we'll talk about something called half-life, which for some of you, Math 30, in fact for all of you in Math 30, that should be a bit of a review for you already, because you would have touched on it in Math 30. So let's talk about those 3 types. What were those 3 types of radioactivity, those natural radioactivities that we talked about? Good. We got alpha decay, beta decay, and gamma. Alpha decay produces a particle that we call an alpha particle. Another symbol that we could write for an alpha particle would be 4,2He, because in the end, 2 protons and 2 neutrons is simply a helium nucleus. It's the same thing. We call it an alpha particle because of the way that it's produced, but it's the exact same thing as a helium nucleus. It's indistinguishable from a helium nucleus. Now, we also have beta decay. Now, there's 2 kinds of beta decay that we'll talk about. Beta minus decay, which of course means an electron has been ejected, and we've got beta plus decay, which means, what's this one? What's this one? Notice I didn't put 0 plus 1 p. That would just be confusing because it's not a proton. Proton can't be 0 plus 1. A proton would be 1, 1 p. This is a starts with a P. Anybody? Positron. It's the antiparticle of an electron. Then, of course, we have gamma decay. Gamma decay occurring down here. Does anybody remember why alpha decay will occur? Remember, it happens in big nuclei, right? Big nuclei. Not going to happen if you have 3 protons. Yeah. Yeah, you get too many protons. Okay, in the end, if you have too many protons, the repulsive force between those protons is too big. And the repulsive force is what wants to break the nucleus apart. There's also an attractive force that wants to keep the nucleus together. But if you have too many protons, the repulsive force wins. You need to improve the balance, the ratio of protons to neutrons. So what you do is get rid of some protons. Now, in the process, you also get rid of a couple neutrons, but in the end, it still improves the ratio. It still improves it still improves the balance of the attractive strong nuclear force to the repulsive electrostatic force. So it doesn't mean it's going to be stable. Just because you get rid of a couple protons and neutrons right here, it doesn't mean it's going to be stable, the product that you get from that, but it's got more chance of being stable. Maybe something else happens to it after that. Maybe it doesn't. Maybe it is stable at that point. Okay, but in the end, you're improving the stability of it. You're getting closer to being stable. What happens in beta minus decay? An electron is ejected. An electron is ejected. You don't even have any electrons in the nucleus. Here's the way to remember this, guys. First one, too many protons. Second one, too many neutrons. Now, something completely different happens here. We're not breaking off protons and neutrons to improve the balance of the forces, because in the end, when you have too many neutrons, it's not an issue of the forces. It's an issue of the energy stability. Okay, it's not quite energetically stable. So what happens is, remember the nucleus club? All the members of the nucleus club get together and say, look, we got too many neutrons. We don't want to kick a neutron out because we like neutrons, but what we can do is change a neutron into a proton and an electron. So the electron goes away because the electrons aren't in the nucleus, right? So it has to leave. It's ejected from the nucleus, and you're left with an extra proton. So in this case, you'd have one less neutron in that nucleus and one more proton. You've just changed it into something else, right? Just like you have up here by getting rid of 2 protons, you've changed it into something else. Kind of like alchemy, right? Making gold from something else. What about beta plus decay? Well, once again, we have too many protons, too many neutrons. This time we got too many protons again. But the solution to too many protons this time is different than it was the first time. The solution this time is to take a proton and change it into something. Let's change it into a neutron and a positron. Notice neutral, positive, negative makes neutral. Positive, neutral, and positive makes positive. Right? So you got to have conservation of charge. That's a fundamental law that must be obeyed. If you start with neutral, you got to end with neutral, and that's why the electron is produced as well. If you start with positive, you got to end with positive, and that's why the positron is produced as well. Yep. Go ahead. I'm not sure what the ratio would be there in order to make that happen, Rucker, to be honest. Yeah, that's right. Yeah, that's right. But that doesn't mean that it's necessarily because there's not as many extra protons. Take a look at the third one. This is gamma decay. And of course, the difference fundamentally between gamma decay and the other kinds is that in this case, we're producing EMR, electromagnetic radiation. Okay? I like to say up here we're producing matter, but only in 2 of the cases are we producing matter. In 1 of the cases, we're actually producing antimatter, right? But it's matter slash antimatter. The bottom one is not matter or antimatter. It's electromagnetic radiation. It's a photon. It's a particle still, but it's a photon of light. All right, this occurs as a byproduct, in a sense. It's a byproduct of the above, byproduct of something that's already happened. The nucleus is left excited when something else happens, right? The nucleus is left excited because a neutron has been changed into a proton and an electron. Beta decay has happened. The nucleus is excited. Hey, we just improved our stability, but wait, we're excited. We don't want to be excited. So we go back down to our normal state by giving off some energy. And the energy that we give off is in the form of a gamma ray photon, right? All right, we also talked about the penetrating power and the ionizing potential of these 3 types of radiation. We'll combine these here, combine beta plus and beta minus into one kind of category here for this, because in the end, the penetrating power and the ionizing power is the same for both of them. The only difference between positrons and electrons is the charge. One's positive, one's negative. All right, what about the penetrating power? Let's just rank them in terms of penetrating power. We won't worry about the exact distances or anything like that, but which one has the highest penetrating power? Gamma rays. Okay, gamma rays have by far the highest penetrating power. They can penetrate easily your entire body. If there's gamma rays coming at us right now, they'll go right through. We're not even going to feel it. They'll go right through. They'll do some damage as they go through. Okay, they will. But in the end, most times, our body will repair itself quicker than the damage is done, so we're okay with that. We're okay with a little bit of damage being done as long as the biology in our bodies can keep up with that damage, as long as it can repair itself quick enough. It's only when you get big doses of radiation that it's a problem, because our body can't repair itself quick enough, right? And the damage is done quicker than the reparations are done. All right, so that's the first one. That's the highest amount of penetrating power by far. Okay, and the next one is going to be what? This can penetrate several centimeters of lead or our entire bodies. What's the next highest penetrating power? Beta decay. And that can penetrate maybe a couple centimeters of our bodies, a couple centimeters of flesh. And finally, of course, that leaves us with an alpha particle, which has a very low penetrating power, maybe a sheet of paper. Okay? My clothes would stop the alpha particles. But then we have the ionizing potential, the ability to ionize atoms. They all have the ability to ionize atoms. They all have the ability to turn atoms into ions. And of course, we know what that can do, right? Turn atoms into ions, get inside our body. Funny chemical reactions start happening that we don't want to happen. Okay, we end up getting sick. We end up vomiting. We end up bleeding from our eyes in extreme cases, right? Radiation poisoning. We get organ failure. You end up having cataracts, okay? Cancers, all kinds of crazy things that can happen to you because chemical reactions are taking place inside your body that aren't supposed to be taking place. Which one has the highest ionizing potential? Which one can ionize atoms the best? I use that term loosely, right? The best, because usually we don't want it. Alpha decay, right? Or alpha particles. And of course, beta's the fence sitter, right? Beta's going to be next. It's going to be in the middle. And gamma has the least ability to ionize matter. Okay, we talked a little bit yesterday about using gamma radiation for cancer treatment, right? I told you the story about my cousin when she was your age and had leukemia. She has a bit of a different situation because of the surgery that she had to have. But in most cases, you have cancer treatment, radiation cancer treatment, which, by the way, is completely different than chemotherapy, right? Chemotherapy is chemotherapy. What does chemo mean? Chemicals, right? Chemicals. It's drugs. Chemotherapy is a concoction of drugs. That's what it is, right? It's just a concoction of drugs, and there's different versions of it, and just different concoctions depending upon the type of cancer you have, and so on. Okay? Radiation therapy is completely different. Radiation therapy normally involves firing gamma rays at a tumor, but it does damage the healthy cells as well. How can you kill a tumor, obliterate a tumor, and not obliterate everything before it and everything after it? Remember, gamma rays go through our entire body. If the tumor is right smack in the middle of our body, how do we obliterate that? Without obliterating the other cells? Okay, that's a good idea. In the case of gamma rays, not likely, but there's certain other kind of treatments that you would, yeah. Normally what happens is, remember, gamma rays have, relatively speaking, a relatively low ionizing power, right? That's one of the reasons they're going to be used here. Okay. One of the reasons they're going to be used is because they have a relatively low ionizing power. One is because they have a very high penetrating power. So fire a beam this way at the tumor. Okay, the tumor's in the middle of my body right here. Fire it this way at the tumor. What happens? Well, it does a little bit of damage to healthy cells. It does a little bit of damage to the cancer cells as well. Fire another one this way. What happens? It does a little bit of damage to the healthy cells and a little bit of damage to the cancer cells. Fire another one this way, and another one this way, and another one this way, and this way, and this way. Every which direction. All around it, it does a little bit of damage to healthy cells. But where they all intersect, there's a whole bunch of little bits of damage to where they intersect, right? Which is where the tumor is. So the idea here is, let's minimize the damage to the healthy cells. And for the most part, we do that, right? We do, for the most part, minimize the damage to healthy cells. As I said yesterday, in the case of my cousin, a little bit of a different situation because of how she received the radiation. Okay, the issues that she's faced, in the 30 years following her radiation therapy are going to be a bit more significant, likely, than most cases. All right. Let's talk specifically about the reactions a little bit more. Define a new term. Transmutation is the conversion of one element to another. Now, isn't that what we just talked about? Radioactivity? Didn't we say radioactivity is the conversion of one element to the other? Not exactly, although it's almost semantics. It's almost just kind of a wording thing. Radioactivity is when one nucleus decays into something else. Transmutation is the conversion to something else. So transmutation can occur. You can convert one element to another by a few different processes, including radioactivity. Another way to convert one element to another is by a process called nuclear fusion or nuclear fission. There's different processes that that will allow transmutation, that will allow the conversion of one element to the other. Radioactivity is one spontaneous natural process whereby one nucleus can be converted to another. That's one of the processes under the umbrella of transmutation. So it can happen, among other ways, by radioactivity. Now we're going to write for the next few minutes nuclear equations, which are somewhat like chemical equations, in the sense that we're showing what we start with and what we end with. In chemistry, you'd call it products and reactants, or better, we should say reactants and products, what we start with, what we end with. In physics, we usually call it parent nuclei and daughter nuclei. So what we start with is the parent, and what we end up with is the daughter nuclei, as opposed to reactants and products. But in the end, okay, that's just terminology. If you call it reactants and products, it's probably going to be okay. Just more of a chemistry term, that is, instead of a physics term. Now, the key with balancing nuclear equations, unlike chemical equations, is that you got to make sure that the numbers balance out. The numbers of protons and neutrons balance out, as opposed to the number of atoms. Because remember, atoms can change. In chemistry, carbon's carbon. You got to make sure that carbon on the left side equals carbon on the right side. If you got one on the left side, you got to have one on the right side. You got 13 on the left side, you got to have 13 on the right side. That's not the case in these transmutation equations. Okay, you might have carbon on the left side, it's gone on the right side completely. But the same number of protons and neutrons have to exist on both sides. So we're balancing in a sense like we do in chemistry, but we're balancing different things. We're not balancing atoms, we're balancing parts of atoms, protons and neutrons. We're going to try a couple examples here, and then we're going to set you free to work for a few minutes on this. First one, not in your book, unfortunately, so we're going to have to copy this one out. It says, write the nuclear equation for the transmutation of radioactive isotope radium-226 undergoing alpha decay. If this radium-226 is undergoing alpha decay, then that means we're starting with radium-226. We talk about the parent nucleus and the daughter nuclei. The parent nucleus here, or in chemistry terms, the reactant, would be radium-226. So we're going to start off on the left-hand side with radium-226. Now remember, it's possible you get a question like this where you're not given the atomic number. It just says 226 Ra. Where are you going to find that number 88? Where does that come from? The atomic number? Periodic table, good. So we're given the number here, and you know what? Most times we are, but if you're not, you know where to find it. There's two numbers beside each element in the periodic table. The smaller number is the atomic number. All right, so it's undergoing alpha decay. That means an alpha particle is produced. We don't have an alpha particle causing this. An alpha particle is produced. So it's going to be on the right-hand side, or we'll call it the daughter nuclei side, or in chemistry terms, the product side. Doesn't matter whether it comes first or second. It doesn't matter whether you call it 4,2 alpha or 4,2 helium. Doesn't matter, same deal. This wouldn't work in chemistry at all, right? Because all of a sudden, we've already got something that can't possibly balance out in chemistry ways, right? We've got radium on the left-hand side. We don't have any radium on the right-hand side. You can't possibly balance that in chemistry if you don't have radium on both sides or you don't have an alpha particle on both sides. Okay, but in physics, we can balance it because we're not balancing atoms, we're balancing protons and neutrons. What else is produced here? Well, if we had 88 protons on the left side, we got to have an 88 protons or 88 atomic number on the right side. 2 plus 86 gives me 88. If we have 226 protons and neutrons on the left side, then we have to have 226 on the right side. 4 plus 222 gives me 226. So the product here would be 222.86, and I believe, double check this on your periodic table, but I believe that's Rn right on. Is that right? So Our parent nucleus here, radium-226, this undergoes alpha decay when it wants to happen, right? We don't control that. It happens when it wants to happen, if it's going to happen, and produces radon-222, which I believe, don't quote me on this, but I believe is also radioactive, radon-222. So it would undergo, we're not going to write this out because we don't know what reaction it would undergo, but there would be another reaction that takes place after this one. We call that a chain reaction, when the product of one reaction undergoes another reaction. Right? Does that make sense? Another one here. Write the nuclear equation for the transmutation of lead-214 undergoing beta decay. I should have said beta negative decay here, because there is two kinds of beta decay, right? Beta negative, beta plus. So we should have said beta negative decay. In the old Physics 30 curriculum that was around about 7 years ago, they never distinguished between beta negative and beta plus. You didn't have to know about beta plus. We wouldn't have even talked about beta plus. We just would have said beta decay, and beta decay would have been beta negative. So if you saw a question on an exam, it might not have said beta negative or beta plus. It might have just said beta. You would have assumed that that was beta negative because that's the only thing you knew. You may have a couple multiple choice questions in your booklet that are from the old curriculum and it just says beta decay. If that's the case, you're going to assume beta negative because that's what they meant by that. But if you saw that question on an exam now, they'd say beta negative or beta plus. All right, so you got lead-214 undergoing beta decay. This is my parent nucleus. And then, of course, one of my daughter nuclei, not really a nucleus, I guess, is my beta particle. I got a beta negative particle, an electron produced. Why? Because the nucleus wasn't stable energetically. They switched, they changed. They changed a neutron into a proton and an electron. There's the electron. What else we got here? 82 on the left side, got to have 82 on the right side. Minus 1 plus what is equal to 82? Tough one. Think you're smart? Think you can add really well? 82 plus or minus 1 plus what equals 82? Yep. 83. I'm telling you right now, that is the single most common mistake that people make in this entire unit. Is a lot of people are going to say minus 1 plus, what do you think they're going to do? What number do you think they're going to put there instead of 83? 81. Okay, they're going to put 81. That's wrong. It's got to be 83. Okay, 1 plus 81 would be 82. If it was beta plus decay, that would be an 81. But it's beta minus, so that's going to be an 83. 0 plus 214. Hey, look at that number for a second. We had 82 protons. Now we got 83? That doesn't make sense, does it? Yeah, it does. Remember, a neutron was changed into an electron and a proton. Of course we've got an extra proton here, right? Of course we do. This is bismuth, by the way, I think. Check the periodic table to make sure about that, but Bi, bismuth, I think. Hold on before you switch your page here, because there's actually something else produced as well. Yep. Oh, good question, good question. What happened to the neutron? Okay, it says, what happened to the neutron? Because didn't I say that a neutron changes into a proton and electron? Yeah, there's an extra proton here, right? There was 82 protons. Now there's 83 protons. There was, what's 214 minus 82? Somebody figure that out quick. There was 132 neutrons. What is there now? 214 minus 83 is 131 neutrons. So the total number of protons and neutrons was 214, still 214, but now it's a result of having one more proton, one less neutron. Okay? We're not quite done this one yet, though. In 1930, a guy named Wolfgang Pauli hypothesized the existence of neutrinos and antineutrinos in order to account for missing energy. There's a little bit of missing energy in this. Where does it go? Well, he hypothesized that these tiny little minuscule particles called neutrinos and antineutrinos might be produced. Never had really any evidence to support it at the time, but we have lots of evidence now. In fact, lots of Canadian evidence to support the existence of neutrinos and antineutrinos. Sudbury, Ontario, famous for nickel mines, right? Like deep, 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 deep underground. They've used abandoned nickel mines as laboratories to find neutrinos. Neutrinos are so small that they'll go through just about anything. The reason we search for them deep, 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 deep underground is because pretty much nothing else will go through all the rock down deep underground, but neutrinos will. So if we look for them deep underground and we see something, it's probably not something else we're seeing. It's probably the neutrinos, because they're pretty much the only thing that can go through all that rock. Yep. Yep. In this case, it's actually an antineutrino produced. It's like a kind of a written V kind of, or a shark tooth, or a saber-toothed tiger tooth. There you go. It's a saber-toothed tiger tooth. But there's a little line over it indicating that it's an antineutrino. This would be a neutrino. This would be an antineutrino. With beta-negative decay, you always get an antineutrino. With beta-plus decay, you always get a neutrino produced. Always. Let's do one more here. We want to complete the following nuclear reactions. 3 of them. 3015 goes to 3016 plus what? Plus what? Well, 16 plus what equals 15? Be minus 1, wouldn't it be? 30 plus 0 equals 30, so that would be a beta particle, right? Is that it? There's got to be an antineutrino produced there as well, because it's beta-negative decay. Uranium-238. 238.92 goes to 234.90, and 90 plus 2 equals 92. 4 plus 234 equals 238. That's an alpha particle, right? Or a helium nucleus. Anything else there? Neutrino, antineutrino? Not for alpha decay. Done deal for alpha decay. All right, 13.7 goes to 13.6. 6 plus 1 or negative 1? Plus 1, right? 6 plus 1. 13 plus 0. Okay, what's this going to be? It's a beta particle, right? But it's, well, an anti-beta, I guess you could say. An anti-electron. A positron. Anything else? Yeah, a neutrino, not an antineutrino, just a neutrino. Remember, antineutrinos go with beta negative, neutrinos go with beta positive. I'd like you to take a look for the next few minutes at worksheet number 24 here. I'm not going to give you a chance to finish this, but it's going to give you a chance to work on a few questions, ask me some questions if you're having any trouble with this at all. And then we'll continue on with this process of radioactivity and talk about not the reaction that happens so much like we are right now, but rather how quickly the reaction happens, how often it happens.